Alrighty. Okay. So the mic is picking up and it is, I think it should be recording. Okay. Let me scroll a little bit. Yep. All right. Well, looks like the class is getting a little bit smaller today. And coincidentally, I got the IP filtering to work. I, All right. And on top of that, we are actually starting on a new topic today because we are pretty much done with binary comparison because now we have so let's just kind of backtrack a little bit of what we have already talked about. We talked about the NAND gate, okay? We talked about binary addition, binary subtraction, base conversion. We talked about signed versus unsigned representation. We talked about comparison, both unsigned versus signed comparison. And all we care is whether x is less than y. Okay, but we have to pay attention to how do we interpret the bit pattern? Are we interpreting the bit pattern as a signed number, which means it can go negative, or are we interpreting the bit pattern as an unsigned number, which means it can only be non-negative values? So we talked about all of those already. So this is kind of like a little bit of an odd topic. Some colleges, like Folsom Lake, would put this topic in CISP 440. And according to the CID template, this topic belongs in CISP 310. So that's exactly why we put it here. It's somewhat of an odd topic, because it is kind of alone by itself. Okay, it doesn't really quite connect to all the other future topics, but yet it is an important thing. So the idea is, how do we represent small, tiny, really small values, and how do we represent super huge values? So the first thing we want to do is, as usual, we start with base 10. Okay, so let me just ask, how many people are familiar with the concept of a base 10 scientific notation? Okay, so we got a few people who raised their hand, and I hope the rest of the class at least have some idea of what that is. So we'll start with an introduction of what is the scientific notation. So this is a fairly standard thing that I do. I start with base 10. The discussion itself is starting with base 10, and then we'll start to generalize things so that it will work in base 2 too. All right. So let me pull my tablet into view like that. And then we'll start with something that you should know already, okay? Because the base 10 scientific notation should have been introduced in CISP 360. So you guys can tell me whether that is the case or not. Because if there are enough people saying that nope, we were never taught about that concept, then I might need to have a word with my colleagues. Yes. Okay. So, but different high schools may teach different kind of stuff. So I'll allow a little bit of variation there. So this is actual C++ notation or C notation for 1.23 times 10 to the power of 45. That's what it means. So let me ask, was this syntax introduced in CISP 360? So I see some people turning their head and most people are turning their heads. Okay. So what did they talk about when they talk about floats? Say again? Oh, so just something that's not a whole number. Wow. Okay. So if I were to say this, okay, if I just introduce this as 1.23 times 10 to the power of 45, is that okay? Does everybody understand the right-hand side of the equality? So the little e symbol is really a shorthand. Okay, every time you see some number, lowercase e, and then another number, another integer on the right hand side, it simply means the e is separating what we call the coefficient from the exponent. So 45 in this case is an exponent, but it is the exponent of 10 because everything is in base 10. And then whatever is to the left-hand side of the little e of the lowercase e is called the coefficient. So we multiply the coefficient by 10 to the power of the exponent. So are we good with that math? Okay, all right. So when you look at this and go like, okay, so we can use this notation to save us a lot of time when we have to write really, really large numbers and also really, really small numbers. Okay, I'll give you an example. What is the speed of light in terms of meter per second? Yes. Okay. Okay. So, all right. So this is what I do, because I cannot remember those things either. So what we'll do is go ahead. Yes. Oh, you haven't seen it. You, yes. No, 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 no. I have a huge swap file. Hmm. Hmm? I have swap file, but usually I don't need to get there. Be Yep. Then your computer will be very, very slow, and no one can watch Netflix anymore in your household. Yes. All right. So the speed of light is 299,792,458 meter per second. So let's just call it 300 million. Okay. So every time you want to specify the speed of light, okay, on your calculator, if you have to type 300,000,000,000, that can quickly become a chore. Okay, it doesn't. Why do we have to do that when you can use the scientific notation? So the scientific notation, the corresponding scientific notation, I'm just writing it down here. Okay, and switch back to the tablet so you can see it. Is 3 times 10 to the power of, I think, 8 in this case. Okay. So I think that's a whole lot easier to write, okay? The same applies to mole, MOLE, which is the number of molecules. It's basically a number of molecules. That's how we can uh, start to evaluate density and so on and so forth, okay? And that's 6.23 times 10 to the power of what? Even a lot more than this. So if we don't use scientific notation, then we'll be spending a lot of time to write a whole bunch of zeros. Or if you want to express um, the voltage of a single electron, okay, which is also known as 1 eV, but that's a very, very small amount, okay? Or if you want to express the mass of a single neutron, which is also a very, very small number. So you'd be writing 0.0000, a whole bunch of zeros before you get to any significant digit. So the whole idea of scientific notation is, oh, we don't have to do that, okay? Do we have any questions about the concept of scientific notation? We have a coefficient and then we have an exponent. Yes. No, that's the whole idea. Okay, we start with 10 so that we feel comfortable about it, and then we'll shift to base 2 at some point. Okay? Yep. 9 point, say again. In terms of meter per second squared, yes, on Earth at sea level, because you have to be specific about, what gravity measured where exactly, right? Okay, so all right, so now that we know what is base 10 scientific notation, now we shift to some number that we might have seen before, such as let's try 35.375, okay, and this is in base 10. So the first thing we want to do is to convert it into, guess what? Base 2, okay? So I hope you guys still remember how to convert something into base 2. Basically, we are rewriting this as a sum of whether there's a presence or an absence of a power of 2. In any other bases, you have a quantity of the power of the base, but in base 2, it's either there or not, because the only two digits you can have are zeros and ones. So that makes it very convenient because either you have it or you don't have it. There's no such thing as, oh, we're going to have like three of these and six of those. Nope, would never happen. Okay, so we look at this 35, and I think you guys can quickly do this and go like, oh, there's a 132, and then after the 32, we have a 2 and a 1 that takes care of the 35, and then we have a 0.25, which is a quarter, and then we have an eighth, which is 0.125. Are we doing okay so far with this? Not exactly base conversion, but re-expressing the value as a sum of powers of 2. Is that okay? Now, how quickly can you do this? Maybe not as quickly as I can because I've been doing this for many, many years. But if I ask you, can you do it? What do you think? Okay, okay, cool. So that's base conversion, or at least one important part of space conversion. So now we re-express this as, okay, 32 is 2 to the power of 5. Okay, well, wait, let's hold on a second here because I need to reintroduce some concepts that some of you might have forgotten, which is logarithmic and exponents. Okay, so uh, if I need to find out what this x is, how do I find that out? I just did it mentally. I knew it was a 5, but if I don't know it was a 5, what do I do? Yes. So you have to convert it into logarithmic form, which means the log 2 of 32 is x. Okay? And then you go to your calculator, unless you have a pretty super duper fancy calculator, they usually do not have log of 2. Most calculators have natural log, which also usually is displayed as ln, or base 10 log, okay, which is just spelled out as log, okay. So it depends on the brand of the calculator. It may be a little bit different. So now you go like, okay, so if I don't have a log 2 button, what do I do? Okay, so you can now say x is the log in base 10 or whatever base you want to use of 32 divided by the log of 2. That's all you need to do. The only thing you have to do is to make sure that it is consistent. If this is log of 10, this also has to be log of 10. If this is natural log, this also has to be natural log. As long as they are the same, they use the same base, okay, then the math is fairly easy to work out. Tonight's lab would also give you basically the same um, introduction. So this part is really important. Okay, so if you have never seen this kind of math, then you have a little bit of catching up to do. I hope all of you have some kind of exposure to exponents and logarithmic math. Am I okay with that assumption? All right, cool. So now we look at this and go like, okay, this is 2 to the power of 5. This is 2 to the power of 1, 2 to the power of 0, 2 to the power of negative 2, and then 2 to the power of negative 3. So 2 to the power of 5 is 1 followed by 5 zeros in base 2. Okay. And then 2 to the power of 1 is 1. Oops. I just do the palm thing. And then 2 to the power of 0 is just 1 with nothing. And then what about 2 to the power of negative 2? Do you still remember from the base conversion discussion? In base 2, how do we represent the quantity of 2 to the power of negative 2? Decimal point 0.01, just 0.1. Yep. So we have 0.01 in base 2, which is 2 to the power of negative 2. And then finally, we have 0.001 in base 2, which is 2 to the power of negative 3. That's because this is digit 0 corresponding to the whether we have or not have 2 to the power of 0. That makes this correspond to 2 to the power 2 to the power of negative 1 because it's digit negative 1. This is negative. This is digit negative 2, and this is digit negative 3. So that's all coming back, I hope, from the discussion of base conversion. So you can kind of see, the difficulty of this class, even more so than 440, has to do with the massive amount of connection between the concepts. I would say for of all the classes, this class probably trumps every other class in terms of the number of connections and also the depth of the connections. Yet, if you were to draw this class as a tree, it would be a pretty deep tree. Well, it won't be a tree anyway. It would be a mesh because definitely there will be multiple paths to the same thing. Yep. Did they really? Oh, oh, ah, yes. Well, okay, so I know I'm about to digress a little bit, but I think it is still an important discussion. And I talked to my CISP 440 class, and Ilya was there because he's also in the 440 class, along with a few probably other individual in this class. And I was mentioning how Meta is letting go of 3,600 plus people in the company. I know Meta is a large company, but 3,600 people, it's still a significant number of people. I think somebody mentioned something like it's about 20% of their workforce. And according to the articles that I read, many people within the 3,600 that were fired also received a good review prior to getting fired. In other words, their immediate prior performance review was okay. At least it's not like, oh, you're underperforming, we are going to fire you eventually. Nope. No warning, nothing like that. Okay. So I want to bring it up not to scare you guys, but to kind of give you guys, the information so that, hopefully you will take that in and think about, okay, how am I going to prepare myself by the time I graduate? How am I going to prepare myself to get a job? Okay, or move on to graduate school. But moving on to graduate school is only delaying the inevitable because everybody is doing that too. So by the time you graduate from graduate school, so will everybody else. So it's not gonna help. Okay, so you kind of have to think about what to do to kind of you know address that situation. Now, is this common to all the other tech companies? I have not done any research. So you guys can do some research, like, look at Amazon, look at Google, look at Apple, and see whether they also have a trend of letting go of people. So it is entirely possible this is just a thing with Meta. Okay, it's a one-shot deal. It's not something that you need to worry about. But it can also be a trend of companies starting to integrate the use of AI so that they don't need as many people anymore. Okay, so just want to mention that. So right now we have this number here, 100,011.011 in base 2. That would be the base 2 representation of 35.375 in base 10. So right now, this is just redoing something that we have learned already in base conversion. All right. So now we look at this and go like, huh. So what if I were to re-express, the number by shifting the point to the left-hand side by 1, like so. Okay. So let me just kind of do this. 10001.1011 in base 2. Okay. I know this is not, they are not going to be representing exactly the same value, but can someone tell me what is the new value in terms of as a ratio of the old value before we shift the decimal point to the left by one position. Okay, so one way to think about this is what used to be um, digit zero is now digit negative one. What used to be digit one is now digit zero, and so on. In other words, all of those powers of two just got changed by one. The question is, which way are they changed? Yes, exactly. So this is one half of what it used to be. Okay, by shifting the point to the left-hand side by one position, the new number is now representing the old value divided by two. Now, is that really surprising to you? Well, it should not be surprising, because if I give you a number like 78.15, okay, and I were to shift this point to this side, it becomes 7.815. The two values are now off by 10 times. It's one tenth exactly, but that's because it is in base 10. So in base 10, if you shift the point by one position, it becomes either one tenth or 10 times what it used to be, depending on which way you shift that point. In base 2, it is either halved or doubled because it is in base 2. Okay, but the idea is the same, okay? Because every digit is representing the quantity of 2 to the power of whatever is corresponding to the position. By moving the relative position by 1, everything either gets doubled or they get halved in base 2. So is that okay? So this entire discussion is going all the way back to how numbers represent values. Every digit, okay, is representing the quantity of the base raised to the power that is corresponding to the position of the digit. All right. So I'm hoping that you guys are seeing the connections, because knowing and understanding the connections is actually very important, because that way you don't have to remember a whole lot of things because they're all derivable from each other. Okay, so that means if I want this to be the same as before, now I have to say, we have to multiply the whole thing by 2 to the power of 1. Is that okay? In order to make this equality. Because otherwise, if I don't multiply by 2 to the power of 1, then the value would have been halved. Okay? So let me ask you this question, and I'm going to put something kind of stupid here because you can always say there's a multiplication by 2 to the power of 0 because 2 to the power of 0 is anything to the power of 0 is 1 other than other than 0 itself. Yes. Um. Yes. It will be the base. So if without this part, this would have been like 17 point, yeah, 625 something. I cannot six. Just use a calculator, divide 35.375 by 2. That's what the decimal value would be without the multiplication by 2 to the power of 1. Okay, that is correct. So now we look at this, and it makes sense too. Okay, let me just do a sanity check because I think that's also a very useful technique. Is we kind of guessed, okay, this number here without the multiplication by 2 is 17 point something. Does that make sense to you? Well, let's check it out. We have one of 1 and then one of 16. What is 16, 16 plus 1? There you go. So we know this is 17 point something. Okay, 17 point, this is a 5.5 and this is a 0.125. So it's 625 plus, some really kind of small number at the end. Okay, so now if I ask you, what about this one? I shift the point all the way to the left-hand side, except for the 1. So now we go like, it's 0, 0, 0, 1, 1, 0, 1, 1 in base 2. Now I ask you, what is the power of 2 that I need to put here? In other words, can you count? Okay, so Every time we shift it by one position, we have to increase this power of 2 by 1 in order to compensate the coefficient being halved. Okay, so we go like 1, 2, 3, 4, 5. Okay, so now we go like that. All right. Do we have any questions about this derivation? Yes. Well, we are not dealing with a computer yet. Okay, so we are looking at the representation right now. So the computer, there's no algorithm or any circuitry to process this. This is strictly just math here. Okay, so right now we look at this and go like, wait, Tack, that looks awfully like a scientific notation. We have some kind of a coefficient times whatever the base is raised to the power of some exponent, except everything is 2. It is in base 2, and we are also specifying the exponent of 2. So this is the base 2 version of quote unquote scientific notation. Are we doing okay so far? All right. So generally speaking, this portion is called a coefficient. Coefficient. And then this part here obviously is called the exponent. Is that okay? Now, all of these are coefficients, okay? Starting from the first line, the second line, and the third line, everything to the left-hand side of the multiplication, they're all coefficients. But the last one also has a special name because when the coefficient is greater than or equal to 1, but less than the base, then it has a special name. It is called the mantissa. Mantissa. So this one, okay, is also called the mantissa because a mantissa has to be greater than or equal to 1, but less than whatever the base is. So in base 10, that means you can specify 9.999999 as the mantissa. And in base 2, you can specify 1.111111, and etc. as the mantissa. But that's the range of values you can use for the mantissa. In all the previous rows, because they are not playing by this rule in base 2, so that they cannot be called the mantissa, but they are still coefficients. In other words, a mantissa is a special case of a coefficient. Are we doing okay so far with the terms? We good? All right. So now we're going to go take a look at how lazy tech can be. Because if you thought you have seen how lazy I was, well, there's something new here. This entire module can be summarized by a single link to Wikipedia. Yes. In fact, if you can get to the point where you can learn everything that I talk about in this class by yourself, by reading Wikipedia, I would say yes. That would be like great. Okay, that would be my dream that all my students do not need me to learn anything about computer science. All they need is Wikipedia. Because once you have acquired that kind of learning skill, you'll be ready for anything. Okay? All right. So now we're looking at this picture here. A 64-bit floating point number is also called a IEEE double precision floating point number. Okay, that's just a long version of double. So in your CISP 360 class, did they talk about double versus float or just double? Hmm? That was 400. What about 360? So did you guys talk about float or did you guys talk about double? Uh-huh. Did they talk about either one? They did not differentiate between float and double. Okay, if it's not integer, use double. Okay, well that's okay. Okay, yeah, because they. Go ahead. I thought somebody was trying to say something. Yep, go ahead. Well, they are very similar in terms of the nature. The only difference is how many digits do you allocate for each portion. So in this class, we only talk about doubles, okay? But you can look up the definition of a single. If once you understand the double, then a float is like, oh, okay, it's just a smaller version of that, okay? So now we have 64 bits, okay? All the way to the right-hand side is bit 0, and all the way to the left-hand side is bit 63. So there are 64 bits in this entire thing. And it's color-coded, okay? The pink portion is called the fraction of the mantissa, okay? It only says the fraction here, but it's really the fraction of the mantissa. And then the green part, it says only exponent, but it's actually the biased exponent, okay? And then the sign bit over here is actually just the sign. Okay, so you can kind of see how, from bit 0 all the way to bit 51, those bits belong to the fractional part of the mantissa. From bit 52 to bit 62, that's the biased exponent, and then bit 63 by itself is the sign bit. Okay, so now you look at these things and go like, okay, but what exactly is the value being represented? So Wikipedia has two representations, and I find both of those to be a little bit confusing. Okay, so that's why I go like, I look at these two and go like, maybe I can do a better job of confusing my students. So that's what I do here. Okay, so that is my representation. So we'll go read this whole thing here, all the way from the left-hand side, and then we'll see if we can process that. So you already know what is VS. Okay, it's this, it's the signed value represented by a bit pattern. Okay, VU is the unsigned value represented by a pattern. This is VD, which is the floating point, the double precision floating point number value represented by a bit pattern. And the bit pattern is, in this case, F. Okay, so F as a parameter is a 64-bit string. Okay, basically 64 individual zeros and ones. Okay, is that okay? Just looking at VDF, do we understand what that is representing? Okay, very good. So now we look at this and go like, okay, what exactly does that mean? Let's skip this one in the middle, okay, and go all the way here. -1 to the power of f of 63. What is f of 63 representing using our usual notation? What is that? What does that mean? It means f f has 64 bits. Okay, one bit is a binary digit, a 0 or 1. So what is f of 63? It's bit 63. Okay, that's what it is. Okay, because it's the same notation that we have been using in this class to designate a particular bit of a bit pattern. Okay, so f of 63 is a single bit, which means it can only be a 1 or a 0. So let me finish this and I'll address your question. If it is a 0, -1 to the power of 0 is just 1. On the other hand, if it is 1, -1 to the power of 1 is -1. So this portion by itself is controlling the sign of the rest, which is non-negative. Yes, go ahead. It has nothing to do with endianness in this case, because we are simply saying if you are to lay out the 64 bits, you know, and you look at the most significant bit, that is bit 63 here. Now, exactly how you store the words, okay, to how you arrange that is not relevant in this case. That is correct. No matter how, because the endianness has to do with when the transmission receives the bytes, which byte do I receive first? So there's a quantification in the process, but by the time we get to this computation, everything is already returned back into the original sequence. So we already have pieced the entire 64-bit pattern back into one single chain, one single thing. Yes. Oh, you just confirm it. Okay, very good. Okay, so are we good with this portion? Okay, so now we try to address let's address this portion first, okay? So let me use the mouse pointer so that people who are not currently here can still watch the video and make some sense out of it. Okay, so we're looking at this portion here. So this is 2 to the power of blah, blah, blah. It has a really long expression for the exponent. Okay, so let's find out what it is doing here. We have a sigma, is a summation. I goes from 0 to 10. And then the other part looks similar to base conversion stuff, and yet a little bit different. Because in base conversion, we would not have the plus 52 here, but this one has a plus 52 because we need to start with bit 52. Bit 52 of the bit pattern specifies how many ones we have. Bit 53 specifies how many twos we have, and so on. Okay, and that's why we have a plus 52 over here. But otherwise, you look at this part of the expression, it is no more than just, oh, it's kind of like VU something, except um, we have to offset the bit position by 52 because that's where the exponent is specified. But by itself, this portion, if you look at just the sigma, it is non-negative. There's no way you can end up with a negative value. Does that make sense? All right. And then we subtract and then we subtract 1023 from it. Okay, so the 1023 is in fact in base 10. We subtract 1023 from whatever the sigma is returning. That whole thing becomes the exponent of 2. Yes. That has to do with this is an IEEE standard, and electrical engineers, at least at the time, did not understand signed number representation. So that's how they can make a bit pattern to specify values that are negative. Because if this was up to computer science people or the math people, they would have just used, VS parentheses, which means, we just designate one bit to specify the subtraction of 1024 in this case. But IEEE is, I cannot remember the full name, but it's electrical engineers. So they're the people who usually work with circuits. So, they did not quite, if they, yeah, they could have just used, signed number representation, but they did not. So the 1023 is called the bias. Yeah, so that's called a bias. So every time when we refer to the bias of the exponent in a floating point number in base 2, we are referring to that particular quantity. Is that okay? And it approximately divide, the total number that we can end up here by, so what about one half are non-negative and the other half are negative. So it works similarly to signed number representation. It's just a little bit like ugh, to a computer science person. Okay. All right. So that's the 2 to the power of something. That's the exponent of 2. And now we just have to look at the center portion here. So let me once again use a mouse pointer to identify which portion we are talking about, which is this portion here. And one thing you might notice is, oh, this one is out there. Okay, it is not part of the sigma notation. It is not multiplied by any one of the bits of the by a floating point number. None of the 64 bits is used to multiply the 1 to the left-hand side of the 1 plus. In other words, we are talking about this one over here, which leads to some interesting observation later on. Okay. Anyway, the rest, okay, the sigma notation to the right-hand side of the addition looks kind of like base conversion again, and this time there's an offset that is applied to the bit position. Once again, This is only because um, the this is the fractional part of the mantissa. So that means bit zero, okay? So imagine when I equals to negative 52, okay? What's going to happen to the term that we are adding? When I equals to negative 52, then f of 52 plus negative 52 is f of 0. So bit 0 is representing the quantity of 2 to the power of negative 52, which is a very, very small amount. Is that okay? So now when you say, okay, what if I equals to negative 1? When I equals to negative 1, then we are looking at 2 to the power of negative 1, which is a half. Okay? But which bit tells us whether there's a half or not? Well, you would just say, okay, what about 52 plus negative 1? Oh, it's bit 51. So bit 51, which is the most significant bit of the fractional part of the mantissa, is corresponding to the number of halves, which is exactly what you would expect it to do. Are we still doing okay so far? Okay. So that's it, right? We have a sign, we have the mantissa, because this amount is guaranteed to be greater than or equal to 1, but less than 2, times 2 to the power of some exponent. That is a scientific notation, except in base 2. And also, the actual individual part are specified by either one or more bits out of the 64-bit allocated to a double precision floating point number. And that's about it. Okay, if I want to, summarize, what is a double, this formula, okay, explains it. But of course, I'm not gonna just, end the discussion here. Um, and I'll give you some examples. Okay, so we are going to take a look at the values that we have been working with, and then we'll manually convert it into the bit pattern, and then we'll also double check to verify that, oh, okay, that really is the case. Okay, so we are going to go take a look at the example that we were looking at, which is 35.375, and I'm just going to borrow, what the result that we already have here, which is going to be this part here at the bottom. So I'm going to lasso that part out and then copy it to the next page once I figure out how to do it. There has to be a tool to lasso something out. Okay. Oh, okay. It won't work that way. There we go. Smart lasso. Intelligently extend lasso extension area. Okay, got it. All right, so we'll do the lasso tool and we'll do the smart lasso. Let's see if this works. Okay, and I want to copy that. So that means copy that, go to the next page. Come on, move. Next page. All right. It's not letting me go to the next page. Nope, that's not it. Hmm. Oh, because it's still using the lasso tool. Okay, so I have to get out of the lasso tool, get back into my drawing tool. Okay, so nope. Oh, okay, let me redo that one more time. Lasso tool. Okay, so copy again, and then we go back to the pen tool so that I can go to the next page, and now I can paste. So how do I paste from here? Insert. Nope. Oh, all right, fine. I'm just gonna do it the old-fashioned way, which is just manual. We'll do it manually because I can't work with this tool yet. One followed by three zeros. Okay, that's easy enough. And then we have 1, 1, 0, 1, 1 times 2 to the power of 5, if I remember correctly. There we go. Okay, so now we look at this and go like, okay, how do we figure out all the bits? Okay, first one is the sign bit. Okay, what do you think the sign bit should be? In other words, what is f of 63? Should it be a 0 or should it be a 1? It should be a 0 because the number is non-negative. Okay, so next thing we need to figure out is what about f of 62 all the way down to 52. Okay, can someone tell me like how do we work that out? Remember, this particular bit pattern is the biased exponent. In other words, the actual exponent of 2 is 5. That's what I want. But in order to represent the value of 5, I have to add the biased amount to it and then convert that biased amount into a binary number. So how do we do that? What number are we looking at? So we are looking at 5 plus 1023, and we need to convert it into base 2, but let's get to the value first. So this is 1028, which is 4 plus 1024, which is then 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. That is a 4 plus 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because 1024 is 2 to the power of 10. Okay, you add up these two, okay, then you get the binary representation. So that's going to be 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 2. Okay, so these bits should go to bit 52 to bit 62. Do we have any questions about how I figure that out? Yes, the 5 came from the exponent of 2. So this 5 goes here. The 1023 is the biased amount. Yep, yes. So it always has to be 1023 because according to the IEEE standard, that is the amount that we are looking at. So you can see this amount is fixed. So as long as you're dealing with a double, it's 1023. All right. So are we doing okay so far with this part? Okay. So now we move on to the rest of the bits, right? Yeah, so now we have to figure out, oh, what about f of 51 all the way down to f of 0, which is the fractional part of the mantissa. Yes. Yeah. Yep. Because this is the base 2 representation of the 4, and this is the base 2 representation of the 1024. Because if you have 2 to the power of n, that means you have n zeros after the 1 in base 2. If n is negative, then that means it is um, that absolute value of to the right hand side of the point. All right. So the fractional part of a mantissa really is just looking at the fractional part of the mantissa. It really is just that. So that means this is going to be 1, 0, 0, 0 11011, and then pad the rest with zeros until you have 52 bits. Okay, is that okay? So I'm literally just copying and pasting. This is copied to, oh, the one does not belong here. So this is the rest. Okay, this portion goes here, and then you pad the rest with all zeros. This is all because of the general formula that I described earlier. Yes, go ahead. Bit 63 is a zero because the only purpose of that one bit is to indicate the sign of the entire thing. In other words, this part here really has to do with what I showed a little bit earlier in my notes. This formula is what drove the derivation here. Okay, so if you're looking at this and you're not making a whole lot of connections, then you might need to spend some more time on your own, just to see how everything connects. Yes. Yep. Yes, that is correct. So now let's put the whole thing back together, right? So if I were to put the whole thing back together, bit 63, okay, this is f of 63 is going to be a 0. F of 62 all the way down to f of 52 is just going to be 1000. Okay, I have to count the number of zeros here. 1, 2, 3, 4, 1, 2, 3, 7. 1, 2, 3, 4, 100. And I'm just going to be nice and move this one down to the actual position of where it's supposed to be, which is here. And then from F51 all the way down to 0, it's just going to be 00011 and then just a whole bunch of zeros until you get down to F of 0. Is that okay? So I'm just concatenating things right now. Okay, I figure out the individual pieces. Now just put the whole thing back together. All right. So you guys would look at this whole thing, go like, well, Tech, you could have told us anything, and how do we double check this? Okay, so we'll talk about that first. Second, the first thing is it takes a lot of time to put in like 64 zeros and ones, and it's a very error-prone process. So instead of using base 2, let's use base 64. Not 64, base 16. Okay, there is such a thing as base 64, but we're not going to use base 64. We're only going to use base 16. Okay, so I'm going to switch to another page just to talk about base 16, and then we'll go back to the earlier page. So in base 16, okay, this is base 16. This is base 2. Okay, so in base 2, okay, first of all, do you think 16 is a power of 2? And what power of 2 is 16? 4. Very good. So that means every digit in base 16 is representing 4 bits. Let me say that one more time. Every digit, every base 16 digit represents 4 bits. Okay? So that means the conversion between base 2 and base 16 is nothing more than just a table lookup. You can go either way. You can go from base 2 to base 16, use the table. You can go from base 16 back to base 2, also just use the table. Okay, so now we go for, we specify the base 2 side first. Okay, and you have seen this already in the form of the number circle. Okay, we have 0000001, 0010, 0011, 0100, 0101, 0110, 0111, 1000, 1001, 1010, 1011, 1100, 1101, 1110, 1111. Okay. So if you count, there should be 16 rows here. Okay. So what do you think is the digit representing 0 in base 16? Okay, that seems to make sense. And this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9. And then we are out of actual numerical digits. You go like, well, we can always borrow something from the English alphabet. So we start with lowercase. Well, it's case insensitive. It's case insensitive. So now we go to A, B, C, D, E, and F, and that's it. This is the base conversion table between base 16, which is also called hexadecimal. Hexa is 6, deci is 10, so together it is base 16. So this on the left-hand side, base 16, it is also known as hexadecimal, but in computer science, most people just call it hex. So when people say hex, it is not base 6, they usually mean base 16. And then on the right-hand side is binary, okay, it's just base 2. You can find this table in a much more professionally formatted manner on the internet. Okay, so I wouldn't just take a screenshot of this and cut it out and put it in your notes. It's just way too ugly. But the idea is that, okay. So now when we go back to the earlier slide, okay, now we just look at this whole thing and go like, okay, we just have to chop it up into chunks of 4 bits. But you have to remember, where to draw the line. Okay, that's one chunk of 4 bits. This is another chunk of 4 bits. This is another chunk of 4 bits. Another chunk of 4 bits. Another chunk of 4 bits. Blah 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 blah, all the way down to here. So now for every chunk of 4 bits, you look up the table. Okay, I don't need to look up the table. I can quickly convert between these two bases. So we have a 4, a 0, another 4, 1. This would be a B and a bunch of zeros. Okay, fine. As long, how many zeros are we talking about here? Altogether, we need 64 bits, but every 4 bit is one hexadecimal digit. So the question is, how many hexadecimal digits do we need? Quick, do the division. 64 bits, every 4 bits becomes a hexadecimal digit. So how many hexadecimal digits do we need? No, 16. Hexadeci by itself, actually, coincidentally. So that means we already have taken care of 1, 2, 3, 4, 5 here. So that means we need 11 zeros in hexadecimal. So that means this entire thing, if you represent it as a hexadecimal number, it's going to be 4041B and then followed by 11 zeros. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One extra one. And that's it. So I'm basically saying the binary bit pattern that is now represented in base 16 in hexadecimal, which is 4041B followed by 11 zeros. If you interpret these 64 bits as a double precision floating point number, it would represent the value that we started off with, which is what, 37.375, I think. Go ahead. Huh? No, no, I don't want to convert it into scientific notation because I want to input this exact number into a program so that I can double check and verify that this, in fact, is going to represent the value that we are talking about. Are there any questions about how we got to the hexadecimal number? No questions? Okay, so we're all good here. So now all that is left for me to do is to go, let's go write a very simple program so that we can double check that this math all works out. Okay, so that's the only thing remaining for us to do. All right, so let's switch to a terminal. And not only do I have a lot of tabs in my browser, even my terminal has a lot of tabs. Nah, these are just tabs. All right, so I'm going to have to increase the font size a little bit just so that the rest of the class can see it. Okay, there we go. And I'm going to write a program to do this. So we'll go ahead and I'm going to go to the temp folder. This is not even a very complicated program. So I'll just call this main.c. And then we have the usual main int. Oh, this is where I can introduce a concept that was introduced earlier in the previous class. Do you remember I briefly mentioned there's a header file called standard integer.h. Okay, very good. Okay, if you are nodding, that's good. Okay, you have been paying attention, and I'm thinking that you probably remember the context as well. Okay, and for the people who did not remember, that discussion, you might want to pay some more attention in class and or take notes in class because everything that I talk about here has a relevance. Okay, otherwise I would not be talking about it. Okay, so in this case, I can now write the program. Okay, and I say uint 64 underscore t, which is one of the types defined in standard integer.h. So this is probably, you can guess what it is already. It is representing unsigned integer 64 bits. Okay. Now, if you use this type in any compiler, any C++ compiler, it still specifies a 64-bit unsigned integer. You can use this type when you're using Arduino, which actually has only a tiny little wimpy 8-bit processor, but this particular type specifies exactly 64-bit wide. You can use it on a 32-bit platform, same thing. You can use it on a 64-bit architecture, same thing. So this way, I can specify exactly the width of the integer. Yes. I guess it means it's a type def in C, in regular C, not even C++. Okay, that would not work. That's not how it is defined. All right, so now it's a x equal to 0 and then return 0. Okay, you guys go like, what? What about that hexadecimal number? We'll do everything in GDB. Okay, GDB is your best friend, should be your best friend. If you have not been using GDB, you should think about using GDB for all sorts of stuff. Okay, so I just compiled the program, and now I can do a GDB main. Okay, I guess it's zoomed out just a little bit too much. That may be best. There we go. We list the program, and then I put a breakpoint on line 7. So, GDB is one of those things, where you can actually use it, through the command line instead of right-clicking, on the line number to put a breakpoint and stuff like that. It supports, something like this. Okay, you can do everything in text. And why do you think that is a feature? Because most people look at this way of using GDB and go like, "Ooh, that is awful." But why do you think this is a good thing? Yes, is like a what? It is a debugger, okay, but VS Code has a debugger, and you don't have to drop down to have to interact with the debugger using text. So what is the advantage of being able to interact with the debugger using only text? Yes, I don't think I look smart, no matter what, I don't look smart. There's no way I can look smart. Sounding smart, okay. I can pretend to be smart, yes. No, no, it's none of the above, okay? This, if you can specify something in text, you can turn it into a script, which means you can automate it. If you can automate it, it also means that when you need to go through a whole lot of process, let's say you have a really complicated program and you need to feed like 20 bazillion test cases through the whole thing, and you want to test it, like okay, but I'm not testing the entire program. I want to test the intermediate steps as well. You can script the entire thing using a GDB script this way. Yes, go ahead. Yep. You can do that too, but you can also, if you want to test specific functions inside the program, you can use GDB to feed it like a bazillion test cases just to test one single function. Because it can print, you can inject values into a variable. So this is a really, really interesting interface because if everything is GUI based, you cannot script it, okay? It's not, or at least not easily. But if everything can be specified in text, then you can script it. Yes, you can. I mean, assert is inside the source code itself, right? You're talking about asserting inside the source code, not in the debugger. Mm, I do not know. I have not done that before, but I just ran the program. Okay, R is run, B is set up a breakpoint, you specify the line number, and now the program is paused, has paused on breakpoint one, which is on line 7. And I can now print the value of X, which is not really surprising. Okay, print X. Okay, X has a value of 0. Are you surprised? You should not be surprised. Okay. So this is where I can say set var, set variable x equals to whatever we had before. I have it on my tablet, so I can actually just type it in, 1b, and then followed by 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I would have made the count proud. And if you're too young to remember what the count is, look up Sesame Street, the count. There we go. Okay. So now we go like, okay, tech, show us the value that we started off with. Print x again. You go like, what? That's not what it is. Well, that's because when I print x, x has a type associated with it. And what is the type of x again in the program? You're staring at it somewhere on the screen. It's a 64-bit unsigned integer. In other words, what you're looking at here with the $2, and by the way, every output of the print has a number associated with it, which means you can refer back to an earlier print for something else, okay, to do something else with it. So what you're looking at with $2 is the VU of F and interpreting up to 64 bits. Do we understand what that means? You still have the same 64 bits, but instead of interpreting the 64 bits using VD, which is the intention of what we want to do, this is interpreting the 64 bits as a 64-bit unsigned integer using the VU function that we have talked about in this class. Yes. No, I do not. Well, I want to do it the hard way. So, so here we are, sticking with C, not even C++. This is straight up C. Okay, so you look at this and go like, what should I do? What can I do about this? So some people remember typecasting. I hope you remember typecasting, which is a very important concept. Okay, so you go like, okay, what about this? You go like, that's not it either. That's because by the time the typecast operator works on X, it has already interpreted X as an as a 64-bit unsigned integer. In other words, all you're doing is to convert this number here into a double representation. So it's not helping. They go like, okay, so how do we get to the interpretation of a 64-bit double, okay, a double precision floating point number? So I'm going to ask you, what is this? Okay, so consider this as a quick quiz of how well you remember C++ concepts because you're going to need it. So what is that? What is ampersand x? The address of x, okay? But what is the type of the expression? What is the type of the expression of ampersand x? It is the address of a unsigned 64-bit integer, okay? So I can press the enter key, you get everything, okay? So you can see that we're not even getting, this is the address, okay? So it can be anywhere in the memory space, but this is the type, okay? So now I look at this and go like, well, okay, that's all good. But instead of typecasting the value, I'm now going to typecast the address. In other words, let's look at the same thing, but we will consider it as an address of a double. So that means I'm doing this. And just to make sure that we know, the order of operators, I'm going to do this. So ampersand x is returning an address to an unsigned 64-bit integer. I look at the same address, and then now I say, hey, uh, I know what I'm doing, so why don't you just consider this the address of a double instead? Okay. Most other languages do not allow you to do something like this, but this is C or C++. It allows you to do the same thing too. So now we can go like, okay, let's press the enter key and see what happens. Okay, nothing too exciting. Okay, the address has not changed, but it thinks that it is no longer the address of an unsigned 64-bit integer, and instead it is now an address of a double. Are we good so far? Okay, so the last thing I need to do is to say, tell me who's living at this address. And magically, we have the number because it is about how we interpret the 64 bits. Those 64 bits have not changed. It is still the same as before. It is about how do you evaluate the 64 bits. Which bit is doing what? Okay, that is the shift. So we got everything back. This is a verification that the program or the approach worked. Do we have any questions about this? Yes. Oh, okay, that's easy. Okay, so I will teach you two things. Okay, the first one is more general, which is every time you have a question of how do we do, what do we do in GDB? Okay, so that works in general. It gives you a lot of topics, but specifically we're looking at print. So if you look at print, it will also tell you the formatting stuff is the same as X, I think. So you can print X. Oh, sorry, help X. So this will tell you how to do the formatting. So basically, it is using the same kind of format in a printf. Okay, did you guys talk about printf or just see out in CISP 360? Just see out. Okay. All right. So I'll skip that discussion. But x means hexadecimal, so that means your slash x is going to specify print everything as a hexadecimal number. So now I can say print slash x, and I need x itself this time. So now we get the actual hexadecimal digits back. But for those of you who go like, but I don't like hexadecimal numbers. I really prefer it to spell out everything in zeros and ones because I like to see a lot of digits. There you go. But the leading zero is gone. Okay, by the way, there's no way to force it to print the leading zero. So all leading zeros will be gone by this time. It would truncate all the leading zeros. All right. So are we still doing okay at this point? Okay. And I hope you guys are starting to be convinced at least a little bit about, the usefulness of GDB. Okay, GDB is a very, I mean, it's installed on every single, distro in Linux. It's a very small tool, and yet at the same time, when you are in programming, okay, I don't really care which class you're in. 360, which unfortunately you have taken already without knowing GDB, but some of you still have to take 400 and 430. As long as you're writing programs, knowing how to use a debugger is going to be very helpful. Okay, at least learn enough to set up a breakpoint and and also examine the values of variables at the breakpoint. Okay, just Get those two things done. You can use the GUI, you can use GDB on the command line version, but learn how to use a debugger, okay? Because that is one of the most useful tools for debugging a program. What if someone says, but my programs never have bugs? I'm such a great programmer. My programs never have bugs. Well, I'm just going to say something that's brutally honest. I say bullshit. Yes, go ahead. Well, sometimes I take the med and yeah. Okay, go ahead. Well, generally speaking, any program that you can write the first time and get it right is not worth writing. That's my, view on these things. Most programs that I write, I have a bazillion bugs. I mean, I'm super careless, as you might have noticed already, just from the usual arithmetic operations that I do in this class. I'm super careless, which means most of the time when I write programs, it's filled with bugs. It's riddled with bugs. But I write programs in a certain way so that the bugs are easily contained. So it's very modular, and I practice certain types of practice so that the bugs are very easily contained. So yes, I have plenty of bugs to get rid of, but it doesn't take me that long to get rid of all the bugs. Yes, go ahead. Modular programming is one, but when you use object-oriented programming, it has a different name, but it's the same idea of organizing your program in a certain way so that it's easy to debug. Well, you may not want to leave just yet unless you already guess the correct access code. I know many of you cannot wait to start your long weekend, but the long weekend starts tomorrow, and today is today. All right, so we do have a lab today. I mean, come on. All righty. And I need to publish it, and the access code is IEEE. Big surprise, it is IEEE, and by the way, this time I think I got the IP filtering set up correctly. So by the time I arrive, I think you guys will be all working on it already. And then some other people in this class will be very disappointed.